All right, and now how can we figure out the frequency?
So E equals H nu.
Right, I guess it's better to write it like this. The change in energy equals H. Oh yeah, and your class is using nu for the frequency. All right, and now at this point, we should plug in a positive number for the change in energy because frequencies have to be positive. It wouldn't make sense to put in a negative number here because then we get a negative number for a frequency, but that just doesn't make any sense. The frequency is the number of cycles you go through per second. We can't go through -8 cycles per second. Right. So maybe let's just write the formula like this. And that will avoid any confusion. So it doesn't really matter very much for our purposes in this particular example what sign we got for the delta E, because we're going to plug in the absolute value of delta E anyway. So I'm going to plug in 1.6 times 10 to the negative 18, and then we have to look up H. That would also be given you on the test. So what's that going to be?
6.63 times 10 to the negative 34.
And we can figure out what nu is.
2.5 times 10 to the 15.
Right. Do you know what the units are for nu?
Hertz or second per second.
Yeah, hertz or cycles per second.
Mm-hmm. Wait, so how did we get that? Because we had joules divided by...
I'm not trying to work out the... Well, yeah, we can work out the units.
Because joules are kilograms times meters per second squared, I think, right?
Right.
And then...
energy was also joules.
And then... because it's second squared. Oh, wait. No, because... it's joules times second.
Isn't it just joules divided by joules?
No, because the H constant is joules times seconds. You're left. You have the left.
Oh, it is?
Yeah.
Okay.
So here's what the algebra works out to be. The energy is in joules, but if you look at Planck's constant, the units for Planck's constant are joules times seconds. The units for Planck's constant are joules times second. Then to get nu by itself, we need to divide both sides by 6.63 times 10 to the negative 34 joules times seconds. The joules will cancel, and the units that we'll be left with are 1/seconds, which is the same as hertz. So that would end up giving us here our 2.5 times 10 to the 15 per seconds, or you could interpret this as cycles per second.
Okay, so now that we have that, now we're going to use C equals lambda nu, right? But had we used, had we solved for frequency, wouldn't have that saved us a step?
Yeah. But what you said a couple minutes ago is that your instructor did it with these steps, so we're just imitating those steps. Let's finish off the problem and then we can see what the shortcuts would be. So what will we plug in for C?
3.00 times 10 to the negative 18. I mean times 10 to the positive 8.
Yeah. And we've got our nu, which is 2.5 times 10 to the 15. So we can end up with our answer here.
And then we have to convert to nanometers.
That's likely the case, yeah. So let's see, what did we get? So the answer comes out in meters.
Right.
So they came out, what did you get there?
1.2 times 10 to the negative 7.
And we've been using standard units, so this comes out in standard units, which are meters. You might have to convert that into nanometers, that's right. So how would we do that?
Times by 10 to the 9. 1 second to the 9. So 120 nanometers. Okay.
So you're using this conversion ratio. That sounds good. You're saying that there's 1 billion nanometers in a meter.
Mm-hmm.
That's right. So then you would end up with 1.2 times 10 squared nanometers, or 120 nanometers. There's always two different ways that you can write a conversion ratio. Right. You could have said that the conversion ratio was 1 nanometer over 10 to the negative 9. No, it's 1 nanometer over 10 to the negative 9 meters.
I usually like to make the bigger one a 1 and the smaller one the positive.
Yeah, that's perfectly fine. All right, so either 1 nanometer is 10 to the negative 9 meters, or 1 meter is 10 to the positive 9 nanometers. So what was the answer to the question?
120 meters should be the wavelength.
120 nanometer wavelength photon is
Yeah,
emitted.
nano.
Okay. All right, so here's the basic steps that are involved. So we used this formula here. Now, what we did here is we used this to find the change in energy, and then we used this formula. I erased it, but we used this formula to then figure out the frequency. And as you guys have been mentioning, in your class, you kind of learned a shortcut. And the shortcut was...
We never used it in class. Only, well, my discussion teacher used it once. That's how I knew
Okay.
about it.
Well, you know, I personally think that you get more intuition from doing things this way. But just to say what the shortcut is instead of using a Rydberg constant that is in joules, you can use a Rydberg constant that is in hertz. And if you use the constant in hertz, then you don't get the energy of the photon, you get the frequency of the photon. And then you can just skip this step and go straight to this step.
That's what,
Okay.
what was the question that we had in class? That was related to this?
It was this.
It was this.
I don't think it was.
It was different
helium,
numbers.
it might have been hydrogen or something.
So in the sample exam that I got, they actually did give you two different Rydberg constants, one in
Okay.
joules and one in hertz, so it looks like the instructor would be, at
I
least in
mean,
this sample exam,
If they don't
the
give
instructor
us,
wouldn't care which one you
if
use.
they don't give us the hertz one, then
Yeah.
I mean doing this way is totally.
That's right, and like I said, for a beginning student, I think the way we did it is better anyway, because it just gives you more intuition for what you're actually doing. It's really good to see the relationship between energy, frequency, and wavelength, and to get some intuition for how that works. One big mistake that students make is they think that all they have to do is figure out the energy of a level. Well, we don't have to figure out the energy of the level. We have to figure out the energies of the levels and then subtract them to find the energy change. So you could have done this by finding one energy level and another energy level and subtracting them. This formula is just a shortcut that builds that subtraction right in. We were talking about the things that can be negative. Well, remember that these energy levels are defined as negative. And energy changes could conceivably be negative, but frequencies and wavelengths can't be negative.